The day the Calm family was substituted, this is not just a chemistry lesson. A real-life event that happens to teach you exactly how free radical substitution of alkanes works. Imagine a family living peacefully in a quiet neighborhood. The alkane family. Every carbon atom has all four of its bonds completely filled. No double bonds. No vacancies. That is why alkanes are called saturated hydrocarbons. Their general formula is CnH2n+2. One day, chlorine gas moves into the neighborhood. Two chlorine atoms bonded together. On the surface, they seem perfectly normal, perfectly peaceful. Then one afternoon, ultraviolet light shines on the neighborhood. Not ordinary light. Invisible, powerful, carrying enough energy to break chemical bonds. Suddenly, the bond between the two chlorine atoms breaks, but it does not break unfairly. It breaks equally. One electron goes with one chlorine atom. The other electron goes with the second chlorine atom. This equal splitting of a bond is called homolytic fission. The chlorine molecule is no longer a peaceful pair. Now there are two chlorine radicals. Each radical carries an unpaired electron. And that unpaired electron changes everything. The chlorine radicals become unstable. Restless, desperate, one chlorine radical looks around and says, I am incomplete. I have an electron with no partner, and I will do anything to become stable again. If you enjoy learning chemistry through stories like this, don't forget to subscribe to the channel. It helps us create more lessons that make difficult chemistry topics easy to understand and impossible to forget. Now let us continue the story. This is where the whole story begins. Chemists call this stage initiation. The spark that starts the entire chain reaction. The chlorine radical starts wandering through the neighborhood, searching, looking, hunting for stability. Then it notices methane, calm, peaceful, completely unaware of the danger approaching. Methane sits quietly with one carbon atom surrounded by four hydrogen atoms, like a happy family holding hands in a circle. The chlorine radical rushes forward and grabs one hydrogen atom from methane. Methane is shocked. One member of its family has been taken away. The chlorine radical finally becomes stable. It is satisfied. Its journey is over. But the story is far from finished, because something new has been left behind. The methyl radical. Methane lost a hydrogen atom. Now it has an unpaired electron. Now it is unstable. Now it understands exactly how the chlorine radical felt. The methyl radical looks around angrily. You took something from me. Now I need stability too. The methyl radical starts searching. Soon it finds another chlorine molecule. Without hesitation, it attacks. It grabs one chlorine atom for itself and becomes stable. It transforms into chloromethane. But there is a surprise. The remaining chlorine atom is released as a brand new chlorine radical. A new radical has been born, and suddenly the pattern becomes clear. The new chlorine radical attacks another methane molecule. Another methyl radical is produced. That methyl radical attacks another chlorine molecule. Another chlorine radical is produced. Again and again and again. One radical creates the next radical. The next radical creates another. The reaction seems endless. Thousands, millions, even billions of reactions can occur, all because of one radical formed at the beginning. Eventually, two radicals collide with each other. As in the above reaction, there are two types of radicals formed: the methyl radical and the chlorine radical. So there are three possibilities. A methyl radical may collide with another methyl radical. A methyl radical may collide with a chlorine radical. Or a chlorine radical may collide with another chlorine radical. The unpaired electrons finally find partners. Stability returns. The chain is broken. The radicals calm down. The reaction stops. Chemists call this stage termination. The drama should be over. The neighborhood should be peaceful again. But there is one final twist. The chloromethane that was formed earlier still contains hydrogen atoms. And chlorine radicals are still present. And ultraviolet light is still shining. A chlorine radical looks at chloromethane and smiles. You still have hydrogen atoms. I want another one. The attack begins again. Another hydrogen is removed and a chlorine atom is added. The product changes again. Soon dichloromethane is formed. But the radicals are still there. Another attack occurs. Another hydrogen is removed and another chlorine atom is added. Now chloroform is formed. Still the radicals continue. One more attack. One more replacement. Finally, tetrachloromethane is produced. One hydrogen after another disappears until no hydrogen remains. This is why free radical substitution rarely produces only one product. A mixture of products is formed. If an examiner asks why a mixture of products is produced, remember the story. Because each product still contains carbon-hydrogen bonds. And those bonds can be attacked again by chlorine radicals. The substitutions continue until all hydrogen atoms have been replaced. Now that the entire story is over, let us answer one final question. Why is this reaction called a substitution reaction? Think about what happened throughout the story. Every time the chlorine radicals attacked, a hydrogen atom was removed from the molecule. But that hydrogen atom was not simply removed and forgotten. A chlorine atom took its place. One atom left. Another atom entered. One member moved out. Another member moved in. Hydrogen was replaced by chlorine. And whenever one atom or group of atoms is replaced by another atom or group of atoms, chemists call it a substitution reaction. Let us summarize the entire mechanism. Initiation creates the radicals. Propagation keeps the chain reaction alive. Termination stops the chain reaction. Repeated attacks produce a mixture of products. And throughout the entire process, hydrogen atoms are gradually replaced by chlorine atoms. That is the story of free radical substitution of alkanes.